afternoon, everyone. Welcome to this session on cloud cost optimization for Java developers. So before we get started, just have a couple of quick questions to see what the audience is in the room. How many people in here are Java developers? Okay, let me reverse that question. How many people are not Java developers? Okay, well, he's the AV tech, so Python, right? I'm just kidding. Okay, so next question is, how many people deploy to the cloud currently? Production, test, staging. Okay. And for those who didn't raise your hand, what do you expect to get out of this session? Just out of curiosity. No? All right. We'll come to that later. All right. So, how many people are on AWS? Okay, hold on. Get that light. Azure? Okay. GCP? Okay. Some people raised hands all three times. That's interesting. Is anybody using anything more esoteric than the three major cloud providers? No one's, yeah. Alibaba? What's that? Okay. What are these? Is anyone using IBM Cloud still? No? Okay. All right. Just want to get an idea of what folks are using. So this presentation, the stuff that we're going to talk about is applicable for pretty much any cloud, depending on, there's some variances obviously between the cloud platforms and things like that. But anyways, my name is PRATIK Patel. I'm a Java champion based out of Atlanta, Georgia. I lead the developer relations team at Azul Systems, and you may have read one of the books I've written in the past. And the most important thing is that my Twitter handle on the bottom left. So if you have any follow-ups from this, please let me know by reaching out by Twitter or LinkedIn or WhatsApp or Telegram or Facebook chat. I'm just kidding. Just hit me up on Twitter, okay? Now, I do work for a company called Azul Systems, and we make several different JVMs. That's the only thing we do is we make Java virtual machines. We have an OpenJDK build called Azul Zulu that gets about 150 to 180 million downloads a year, so it's very popular, and it's 100% free. And we also have a high-performance JVM called Azul Platform Prime, which I'm not going to really talk about either one of these, but maybe for a minute or two through this 50, 60-minute presentation, okay? All right, so really quickly on Azul Platform Prime, this is our high-performance VM. We have our own JIT compiler, our own garbage collector, and hundreds of performance enhancements in it. So that's why we get great performance, or our customers see great performance. So for example, with Apache Kafka, just by switching out OpenJDK to Prime, people are seeing 40% increase in throughput, or you can shrink your servers by 30, 40% and push the same load through it. Hence, cloud cost optimization. Again, it's 100% OpenJDK compatible, no code changes, and save on cloud costs. All right. So now, does anyone recognize what this TV show is? So yeah, well, what is it? Silicon Valley. You've seen it, right? Right. So when this TV show came out, I was working at a startup, and I had to stop watching the TV show because it was way too much like real life. I'm not kidding you. So, but the reason why I have this up here is because for years, as software developers, we've been told, go fast, deploy as quickly as possible, use as many resources as you need to in the cloud, right? I don't know can I be over here? Will the camera catch me? Oh yeah, I see the camera moving. Okay, I'll be a little dark, but that's okay. So for years and years, it's been like an open wallet, right? Do whatever you need to do to get the apps out, to make fixes, to introduce new features. And now all of a sudden, I don't know about you, but I've been asked for the projects that I work on that you need to start thinking about, we're spending too much on cloud. We need to start reducing this cloud cost. Now, how many people in this room have had that same pressure recently? Okay, I figured probably everybody here. And if you haven't, I would not be surprised if you don't get that pressure, because it is coming now, right? So here's a question for you. Okay, what's the best way to reduce cloud cost? And what's that? Not using it. That's actually a great answer. So what would you use instead? Use your PC or your PC that's under your desk. Yeah, there you go. So anybody else want to take a crack at this? This is not a trick question, by the way. Trick questions come later. So scale to 0. That's actually a really good answer. Yeah. Anybody else? Don't forget to shut down stuff when you're not using it. This is actually a really big one. So I don't know why I'm giving this presentation. You've hit like almost all the major points already. So any other thoughts? How do you reduce cloud? As a developer, an architect, or a DevOps person, how would you reduce cloud costs? Anyone else? We had some good answers so far. So Obviously, the right answer, Elias is my friend. He's sitting on the front. Is just to turn off all your servers. Anyone remember what this movie is, by the way? Yeah, Office Space. Okay, if you haven't seen it, this is like the Star Wars for computer nerds. So okay. Anyways, all right. So the real answer actually is it depends on your application. So in this session, I try to cover like a broad spectrum of things in terms of strategies that I've seen and that we've recommended to customers. What are our customers doing to reduce cloud costs? How are we helping them reduce cloud costs and stuff like that? And the thing is it really depends on the application, right? So if you're building a Spring Boot RESTful application, the way that you reduce cloud costs for that is going to be very different than if you're running a data intensive type of application, just writing with pure Java, or if you're using like Spring Data or whatever, right? Or like Apache Kafka or other big data tools, right? So it really depends on your application. But I hope to give you enough information in here based on the tons of research that I've done working with customers, et cetera, to give you an idea of how other people are doing it so that maybe you can take a few of these points back to where you work and try to save some money on your cloud cost and make your boss happy. Okay, all right. So the real answer is, of course, there's no one size fits all for this. All right, so let's briefly go over the topics we're going to cover in the next 44 minutes. We're going to talk about application architecture because this is super important. That leads to a discussion on what's the architecture actually look like. Is it PaaS, CaaS, cloud functions, or using Kubernetes? Okay. Then we'll spend a little bit of time, since this is a Java conference and everybody in here is a Java developer, on how the JVM specifically can be tuned, or at least how you think about how Java applications in the cloud can be managed from a resource perspective. And of course, resource I use as a synonym for cost. Okay. We'll also talk about dealing with variable headroom, basically variable load headroom. Do we over provision, or do we try to use elastic computing? And we'll do a quick review of that. Okay. But before we get to that, let's talk a little bit about cloud pricing. Okay. So here's a question for you. Let's set some assumptions here real quick. In the last 5 years, do you think that the cost of cloud compute and memory, okay, again, making some assumptions, last 5 years, has the cost of compute and memory on all the major cloud platforms gone up, down, or stayed the same? So let's start with up. How many people think it's gone up in the last 5 years? Wow, okay, that's an impressive number of folks. How many people think it's stayed the same in the last 5 years? Okay, so a few folks. How many people think it's gone down over the last 5 years? Okay, a few folks. Okay, so how many of you have heard of something called Murphy's Law? Not Murphy's Law. Who's the guy from Intel? Someone help me out. It's Moore's Law, thank you. Moore's Law, which is basically the number of transistors that can be packed onto the die doubles every 18 months, which has meant over time that the amount of CPU horsepower nominally doubles or goes up by 50% every 18 months. That's why 10 years ago, you would buy a new computer every 2 years because the new one was much, much faster. But what's happened over the last few years, as you know, is that Moore's Law is kind of outdated now, right? We don't see that 50% or even a huge jump in compute power on the same chip die size that we used to. So it kind of makes sense if you think about it that, okay, we're not getting more, better, cheaper compute power right now. So yeah, maybe cloud compute cost maybe goes down a little bit, maybe it stays the same, maybe goes up, right? The real answer actually is over the last 5 years, again, that was the assumption, is the cost of compute and memory, for that matter, has actually stayed mostly the same, okay? So if we look at this chart, and there's a reference to the chart here in the bottom corner. Okay, so you can see, and this is basically AWS, right? So this is US East getting a virtual machine, memory, and compute, right? But you can see that over about the last 5 years or so, it's mostly stayed the same. Now, this inflection point right here is when AWS and Azure introduced Graviton and EPYC-based CPUs. Is everyone familiar with what Graviton and EPYC are? How many people know what Graviton is? Right. So how many people have a MacBook, a newer MacBook with the M series in it? Right. So your newer series Macintosh computer uses ARM64 architecture, which is a little bit better at the cost performance ratio. And Graviton is basically an ARM64 CPU. Okay. And EPYC is Intel's version of basically it's AMD's version of x86 CPUs, right? So that's you can get them on desktop and laptops, and they also have them for servers, and it's called EPYC. But the point here is that at that point in time, there was a pretty substantial drop in what it would cost to get CPU power on demand. But as you can see, it's actually stayed the same. And this is really interesting. Now, I've asked this question before, and the feedback that I've gotten is that, I asked the question, why has it stayed the same instead of going up, right? There are a lot of factors here. It costs more to build data centers today, or has over time. The cost of electricity has gone up, et cetera, et cetera. There are a number of different factors. Or it could just be that the cloud providers see the demand and then they know how much they can charge for it, so they do, right? It's a business after all. All right. So we talked about that a little bit, but when we think about the money that you spend for cloud, it's a number of different things, right? It's compute, it's storage, it's memory, shared services, APIs, and databases. So in this session, we're going to kind of focus more about CPU and memory and less about these other things. But all these things come together. And we'll talk about these other things also in terms of an overall strategy for bringing down your cloud costs. Okay, let's spend a few minutes talking about scaling, because I think this is important to understand, especially in terms of architecture, how you build an application that can be a little bit more, a little cheaper to run on the cloud. Okay. So here's a question for you. What's more efficient if you're building a brand new application today, or maybe you already have some applications, right? What's more efficient from a CPU and memory point of view? A monolith or a distributed compute environment like Kubernetes or Cloud Functions or whatever? What do you think? Monolith is more efficient or less efficient? More efficient, okay? How many people think a distributed architecture would be more efficient? Okay, right. So the answer in this case is that it's typically monoliths are more CPU and memory efficient. And we'll look at that here in just a second, right? So when we think about monoliths versus distributed, obviously we're talking about vertical versus horizontal scaling, right? Now, horizontal and vertical scaling, does everyone know what those two terms mean? So most people do, but I'll just do a very quick review for those of you who don't, right? So it's summarized on this slide. Vertical scaling means that you add more CPU and memory. Horizontal scaling means that you add more servers that, of course, have CPU and memory, and you scale out this way as opposed to packing everything onto one server. Okay, that's a very basic definition of it. And so we have those two different scaling dimensions, right? So when we do vertical scaling, we add more CPU, we add more memory, we may add more network cards to have more interconnect or whatever inside of that thing or to the outside world, right? And then when, horizontal scaling, of course, is when we add more servers and we have something in front of them that distributes load around them, right? So now vertical scaling is linear to a point, because at some point you hit up against the number of CPUs or the amount of memory that you can add to a server. And of course, how fast is the backplane on the server? How fast is the memory, et cetera, et cetera. All those things play into how far you can push a single server to do vertical scaling. Horizontal scaling is linear at scale. So you can theoretically, add as many servers to this cluster as you want. And the key thing here is that horizontal scaling is also elastic, right? So when you buy it, if you're doing vertical scaling and you add more memory and you add more CPU to a server, that's not elastic. Elastic meaning you can't change it very easily, right? Whereas when you do horizontal scaling, nowadays it's pretty easy to say, let's just add another server, another 2 or 3 servers into this cluster and tell our load balancer or whatever it is to distribute the load between those, okay? So that leads us now into a conversation about architecture in terms of what it means for your application, how much it costs to run it. Okay, so this is how I visualize this. Again, there's a number of different ways that you could look at this, but this is like the slide that puts everything together in terms of architecture, though we'll dive in a little bit deeper. Okay, on the left side, we have a monolith. On monoliths, we have to typically vertical scale. Right? You can do distributed monoliths, of course, where you just say, I'm going to have 5 servers or 10 servers, put a load balancer in it, but it's pretty hard to go and scale that up and down, right? But that's, not so much a monolith. Now you're kind of getting more towards the right side of this, right? And of course, monoliths are vertically scaled, but they don't typically tend to be elastic. It's hard to add and remove CPU and memory from an existing server. In the middle, we have microservices. Everyone's familiar with this. How many people build with or deploy to production microservices today, out of curiosity? Okay, that's pretty much everybody in the room. Okay, and on the far right of the spectrum, we have PaaS, which is functions as a service, otherwise known as cloud functions. Now, as you move to the right, we're doing horizontal scaling, and this is very elastic, right? And if you're familiar with cloud functions, you know that cloud functions are kind of the ultimate in elasticity because they can auto scale up and auto scale down depending on demand, or they can scale to zero. Someone mentioned scale to zero earlier, which is a great way to save money because you're not running any services or you're not running any infrastructure when there's no load coming in. Okay. So anyways, this is our app spectrum. And what do these different things mean? Okay, so again, if you have the ability to be elastic, even though there's more overhead, it's less efficient. It actually works out better for cost control because nobody has load that's even throughout the day, right? Load goes up and down throughout the day depending on your application. Say you're building a trading app, your finance trading app will be doing nothing between 4 p.m. and 8 a.m. the next day. But during those hours of 8 a.m. to 4 p.m. will be very busy, and especially at the beginning of the day, you get all these orders that are backed up that need to be filled, so you get a big peak, and then it'll kind of level off during the day. Okay, so again, elasticity is the ability to scale up and scale down, sometimes automatically. Okay, and of course nowadays a lot of people talk about doing this kind of elastic compute with Kubernetes, but in my opinion, Kubernetes adds quite a bit of complexity, which of course complexity adds to the cost of an application, not just in terms of infrastructure and all the DevOps stuff that you need to do, but also in terms of the actual programming that you need to do to be able to have this microservice kind of environment that makes, that has a mesh of calls between them. All right. So of course there are other options. There's also platform as a service, which is basically just give something basically just a VM. How many people have heard of CaaS before? Right. Okay, good. So only a few people. So what CaaS means is containers as a service. So this is what you have on AWS as AWS Fargate, what you have on Azure as Azure Containers, and on GCP it's Google Cloud Run. So a CaaS is basically you take your application, you put it into a Docker file, you give it to Amazon Fargate or something, and you say, go run this app for me and go deal with all the bullshit because I don't want to. Basically, it'll scale it up and scale it down, similar to what Kubernetes auto-scaling can do, but you don't have to run a Kubernetes cluster, right? Similar to EKS, except a little bit simpler. Okay, and then of course the ultimate in scalability for the cloud are cloud functions or functions as a service. They typically have auto scaling and scale to zero and all sorts of other things that allow you to build an app that is super scalable. But we'll talk a little bit more about cloud functions, and there's an inflection point at which cloud functions are not any cheaper than the other options that we've talked about already. So it's great having a pay-per-use model, a very, very granular pay-per-use model with cloud functions, but when you have a lot of load and you have consistent load, it's actually cheaper to just roll your own VM out or use a CaaS or use Kubernetes. But we'll talk about that in a bit. Right. So we just said all this stuff about how microservices and cloud functions are better for elastic compute and et cetera, et cetera. But this is an actual tweet that came out in January. So you can look up the person and find this tweet. But you don't need to read the whole thing. I've summarized it for you at the bottom. Basically, what they did is they compared a modular monolith with a microservice. And what they found out was that it reduces application latency by up to 15x and can reduce cost by up to 9x. And if you read the text in here, you can see that this is the interesting part here. A recent paper by authors from Google found blah, 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 right? So it's kind of interesting that for years we've been talking about, yes, you should do microservices and do distributed computing because you get elasticity and flexibility and you have smaller units that you can roll out faster. But it makes sense that something that's a monolith would be much, much more efficient, right? Does anyone want to guess why? Or, you probably haven't read the paper. How many people have read this paper, by the way? Anybody yet? Okay, so you read the paper, right? So what in the paper do they say? What makes a modular monolith so much more efficient than a microservice or cloud function?
One of them that strike me like the operational cost of it. Apart from the CPU and the other hardware cost, the operational cost was significant in maintaining such large cluster of tiny services. So it's a kind of a middle state from monolith to a microservices that we are calling it like modular monolith.
Right. That's right.
Your overall footprint and it's better in like operational cost.
Yep, that's exactly right. Right. So the other part of that is that when you're building a microservice or cloud function, you're making a lot of calls between services. So what needs to happen in that time when you make these operations? You have to deserialize and serialize data, right? Which incurs, and then you have to go over the network, which incurs a very large cost. in terms of not just latency, but also compute, right? Serialization and deserialization is not free, especially if you're sending large amounts of data, even small amounts of data with lots of requests. So anyways, I encourage you to go check this out. I have a reference to this at the end of the slide deck that you can check out and read, and you can say, yes, we should still be doing monoliths, right? I'm joking, of course. Okay. All right. So let's spend a bit of time talking about JVM considerations, and specifically, what is it that we can do when we look at this through the lens of a Java developer or architect or Java DevOps person. Okay. Now, I probably don't need to have this slide for the people in this room, but I'll say it anyways, right? Java is actually a very good language for cloud. Don't let the Go people tell you otherwise. Okay. Java is actually a very good language for the cloud. Okay, and part of the reason for that is Java is extremely power and cost efficient. Believe it or not, I have proof. I'll show you in a minute. Okay, the other reason is, and this is more of kind of less of a technical and kind of a team organizational thing, is that Java is an extremely flexible language. You can build small apps with it, or you can create gigantic apps with it, just because of the nature, all the great things in Java: object orientation, package system, package management with jar files, Maven, etc. Right. Another thing, of course, is that Java is great for all different types of things. Right. You can build large apps with it. You can do data processing with it. You can build mobile applications with it. Again, I'm preaching to the choir, since everyone in this room is a Java developer and loves Java already. Okay. Now, one of the things that we have to consider is when we're deploying Java to the cloud, or even if you're deploying into your own data center or your own infrastructure, one of the great things about Java is that because of the JIT compiler, Java actually gets more optimized or more efficient over time. Right? So what the JIT compiler does, as everyone knows in this room, is it takes your code and it finds ways to make it more efficient. So depending on your application, it can become very, very efficient. But it does, when we'll look at this in a little bit more detail in a minute, right? The JVM, because of the JIT, it actually becomes more efficient over time, which is great. Okay, but what we do have to deal with that is that the JIT does take some CPU horsepower. It does take some time to find the optimized code paths and then inject new bytecode into your application to make it more efficient, to make it run faster, right? And that obviously, it needs not just CPU resources, it needs time to be able to do that. Okay, so let's look at how energy efficient or cost efficient, same thing in this scenario, Java is. Okay, so I have a link to where I've got this study from. But what these folks did is they wrote a moderately complex application, and they wrote it in all these different languages, and they exercised it many, many times, and they hooked up a multimeter to the CPU and the memory bus to see how much memory the CPU and memory was consuming as they ran this endurance test. Okay. So as you can see, Java comes in pretty cost efficient or memory efficient, energy efficient. That's probably what, about 40 joules for this specific run. So the thing is called, the test that they ran is called FASTA. Again, there's a reference to it here that you can go and check out. Okay. And right, so this is specifically for VM-based languages or virtual machine-based languages, right? So you have C#, which, as you can see, I know this is a Java conference, but C# is a pretty good platform with the CLR and everything. It's not as good as Java, of course, since this is being recorded. Let everyone know that. But you get the idea, right? So, and again, this just happens to happily translate into like cloud cost, because the more efficient something is in terms of CPU and memory, the less CPU and memory you have to give that application for it to run. Okay. So, anyways, just want to give you a sample of that, and of course, I had to throw in this the same chart that has Perl in it because I hate Perl. How many people still build with Perl out of curiosity? Anyone have to? Okay, good. I'm glad that we don't have to be tortured like that anymore. But anyways, there's also, you can see JavaScript is here. JavaScript comes in, if I remember correctly, like close to 80 or 100. So it's not as efficient as Java, but you can see, I just threw this in here for, to give you an idea of like what and these are obviously interpreted languages, as you can see here. Okay. All right. So we've talked about why Java is great for the cloud, but what are some JVM specific optimizations that we can look at in terms of making our Java applications more efficient for the cloud? So before we get to that, let's review some JVM runtime basics. Okay, so what I'm going to do is I'm going to flip to my little drawing app here. And oh, it works. Okay. All right. So let's think about what happens when we start up a Java application and as we're executing a Java application over time. Okay. So we have two axes here. Oops. This thing is not on. Let me turn it on real quick. Thought it was on. Okay. I'm just going to have to draw with my finger if this doesn't work. Okay. Here we go. All right. So we have two axes here. Right. This axis is time. And on this axis, what we'll do is we'll look at CPU utilization. Okay, so what happens when you start up a Java application? The JVM itself has to boot, has to load all the classes, et cetera, right? So what we see initially for our application is that we go up very quickly and we're loading all our stuff. And let's just use Spring Boot as an application. Does anyone not know what Spring Boot is here? Okay, figured everyone does, right? And it doesn't matter if you're talking about like a Java E application, or sorry, Jakarta E or Spring Boot, or if you're using Quarkus or whatever. This graph looks pretty much the same for everything, okay? So at a certain point in time, you've loaded up all of your Spring or whatever application. So this is what I call ready for first request, okay? So this is the point in time where your app is ready to start serving requests, right? So what happens after this is that the JIT compiler kicks in and it uses CPU cycles. Actually, let me redraw this. I didn't give myself enough headroom here or enough space. Go back. Okay, CPU. Okay, so we go up very quickly and we reach a ready state, right? This is ready player one, whatever. And then our JIT compiler kicks in and it's optimizing code. And at certain point in time, what happens is we reach a place where the JIT compiler can't really optimize too much more, okay? So let's say that point in time is somewhere around here where we reached 95% optimized code. Okay, so we reach about 95% optimized code at this point in time. So our CPU utilization is actually lower when we look at it right here. Okay, so if we draw this line all the way to here, and our peak CPU utilization is when our JIT compiler is there, and maybe there's still some setup and other stuff going on as our application is kind of warming up. Okay, now the main thing that we want to try to fix with this curve is that we reached peak CPU utilization, peak efficiency. Okay, the JIT has done its work. Again, the JVM is an amazing piece of machinery that optimizes the crap that we write and makes it run faster, right? So what happens is that after we reach this peak, this part right here is basically wasted overhead, because when we typically deploy an application, we say we're going to give it 8 CPUs and X amount of memory, right? And then once that's running, we can't change the amount of CPU cores that are assigned to that VM. Not typically. There are different cases here, right? But this basically is wasted CPU allocation to you, i.e., this is where you're wasting money. Okay, because you don't, maybe instead of having 8 cores at this point in time, right, you only need to have 6 cores. So you could reduce by 20% the number of CPU cores you've assigned to this application, right? So that's one thing we'd like to fix. But there's actually, and this is this specific part of the problem is extremely hard to fix, by the way. But what's a bit easier to fix is, as a developer, what we do is we tend to over provision because we don't know what the peak is going to look like, right? This is just kind of a simplified diagram. During the day, your application hits a peak and then, load goes down, it goes up, etc. Okay? So what we tend to do to make sure as developers or DevOps people is we will over provision the amount of capacity that we have in this specific virtual server, right? So that means that we'll say, you know what, we might hit a peak like up here somewhere during the day, but let's be safe and let's set our number of CPU or memory resources at this level, right? And so what we've done is we have over provisioned our service. So, and again, this is essentially also waste or extra money that we're spending that we don't necessarily need to be spending. Okay? So, let's ask some questions now. Let's talk about the over provisioning part first. What can we do to help with this over provisioning part? right? Because again, we're just now, our boss is giving us pressure. We need to make these apps use less money when we run them, okay? So what can we do for this over provisioning part to like not spend as much money on it? Any guesses? There's not a trick question. And there may or may not be right answers here, so. Okay, so someone said they do elastic scaling. That's 100% true. Okay, but even within the VM, you have to accommodate for the peak. So one way to look at this is if your unit of the module that you're deploying is smaller, then the amount of over provisioning that you have to do will typically be less. Okay, so that's one way to look at it. Sure. Okay. Anyone else want to take a guess at it? Unfortunately, there's no real right or wrong answers. Everything is app dependent at this point. Okay. Now, there is something called CPU boost. For example, I believe that's on AWS. Where are my AWS people in here? Right, there are a few. Right, have any of you guys ever used the CPU boost feature for a VM? Right, so there you go. There's loads of people who've used AWS but have never used or maybe even heard of CPU boost. Now, what CPU boost does is it gives you extra horsepower for a set amount of time when you start up your VM and your application. Right, so that can be useful because now you can just say, I need an extra 2 cores for the first 10 minutes of this application and then bring this down, right? Bring it down to 6 cores or something like that. Actually, I have another question here. So this point in time where I said the JIT is 95% optimized, how long do you think it takes to reach this point in time in an application? Let's make some assumptions. Let's make a few assumptions first. Okay. Oh, let me put this pen down so I'm not pointing it at you. Let's say that we have a 10 or 20,000 line Spring Boot application running on modern hardware. I don't know, pick your version of Spring Boot. Spring Boot 2.7. Again, media-sized application. 10, 20,000 lines of code, maybe a bit more, approximately that much. We put it under full load. We exercise most of the code paths in that app. How long do you think it takes the JIT to get to about 95% efficiency in terms of what it can do to make that application more efficient? How long do you think it takes? Around 1 day. That may be a bit too long. 2 minutes. Okay, someone said 2 minutes. Someone said, who said 20 minutes? 20 minutes. Okay. You're not allowed to answer questions, Dimitri. Dimitri works for a JVM vendor. So that's actually that's approximately the correct answer. It would, yes. Well, that's why I said we're putting it under heavy load, right? So that's one of the assumptions, right? So we're exercising most of the code paths over and over again, yes. So, but Dimitri is right? So typically for an application like that, with standard OpenJDK JIT, it can take 15 to 20 minutes to reach about 95% efficiency in terms of what the JIT compiler can do to make code efficient. Okay, so in Azul's Platform Prime, our high-performance VM, we have our own JIT compiler called Falcon, and it's much more aggressive than what's in OpenJDK. So that one may take 20 to 30 minutes to reach peak efficiency of that 95%, around 95% efficiency, but it does better job at optimizing code, so it produces much more efficient bytecode than standard JIT, right? Again, just to give you an amount of time. But that will come in a little bit handy in a few minutes when we talk about what do we do when we have elastic compute and we're scaling things up and down in a Java environment. Okay, so again, key takeaways here: over provisioning, right? We try to bring this down, or as you know, we try to be less risky and bring this, or let's more risky. Sorry, not less. Take a little bit more risk on and say, let's bring that top line down, and instead of like over provisioning by 10 or 20%, maybe only over provision by 5 or 10%. Of course, you have to try all this out and make sure it works first. Okay, and then what can we do about this, right? So our JIT compiler has done all its work. The JIT compiler is not using CPU, and on top of that, the code paths are more efficient, so our app is running overall more efficient. What can we do about this? Right. Okay. Let's flip the question around and let's go into the area of like just wish list or theory. What would you wish could happen in this case to solve this problem? Right. Optimize ahead of time. Right. There's AOT, but AOT is just compilation, getting the setup part of it. But yes, optimize ahead of time. Yes. Change the what? We could, yeah, we could do what I was talking about earlier, which is AWS VM's ability to have extra horsepower at the beginning and then scale that back at runtime, right? So, but someone nailed it, right? What if we could provide this Java virtual machine with a pre-warmed up JIT compiler, okay? Now, there is work going on in this specific area. IBM has something called the Network JIT server, which what you do is you set up a server in the background, and it will go, oops, that's not supposed to happen. It will go and serve up a warmed up JIT, right? So all the stuff, optimizations that need to happen will be provided to the JVM. So the curve will look less like that. And I'm just going to draw in this small space right here. If this hadn't turned off again, okay. It'll look more like, right? So the bump there will be a little bit less right here, okay? So that's what we want. And of course, Azul's high-performance Java virtual machine called Platform Prime, it has something called Cloud Native Compiler, which can also do the same thing. So the idea is you set up the server in the back, which has your application's code. It serves up a pre-warmed up JIT along with another tool that we have called Ready Now, which serves up the JIT already, so you don't have this wastage that we're talking about here in the middle. Okay, but those tools are proprietary at this point and not part of OpenJDK. Okay. All right, let's get back to our slide where draw a CPU chart here. Okay, all right. So a couple other questions you have to ask yourself as a developer. How much does the JIT matter for Elastic, right? If we have short running applications that may only run for 10, 20 minutes and then they get scaled down or we recycle them and depending on what kind of setup we have, is that something that we need to think about? Maybe, maybe not, right? Depends on the size of your application. All right, what's the warm-up time? Do we need to think about garbage collection? Now, unfortunately, this bullet point right here is an entire presentation, okay? And one of my colleagues actually has a presentation on the different garbage collection algorithms. His name is Garrett Grunwald. If you do a Google search for him, you'll see his presentation out there. And I think one of mine is also out there. I have a separate presentation called garbage collection algorithms for the cloud. But again, that's a full 60 to 90 minute presentation. So we won't spend too much time on that here. Okay. But a long JIT warm-up means short-lived processes benefit less from the JIT, right? But of course, there should be a big asterisk here. It depends. If your application is 1,000 lines of code, the JIT will optimize that probably in a minute or two. So you're still getting the benefits of having that JIT compiler and getting that optimized code, i.e. being able to have less CPU and memory horsepower for that specific thing, okay? And I talked about a couple of these things already, right? I talked about some proprietary tools that Azul has called Ready Now and Cloud Native Compiler that helps with that. But that's specifically the pre-warmed up JIT. There's also a technology called CRAC or CRAC that allows you to do instant startup or near instant startup for Java applications. Spring Boot 3.2 just introduced support for CRAC. How many people have not heard of CRAC in this room? Okay, so that's a fair number. I have a presentation on this online also that you can go have a look at as well as my colleagues. But essentially it gives you, I'll just summarize it for you in 10 seconds. The Spring Pet Clinics demo application normally would start in about 4 seconds. When you crackify, I hate the word crack, by the way, when you crackify the application on it, or sprinkle some crack, as I like to say, sprinkle some crack on it, it will take that 4 second startup time down to 40 milliseconds. So 2 orders of magnitude approximately faster. Okay. But again, that's a full 60-minute presentation. So I don't want to get into that here. I'm going to cover some of our topics. Okay. All right. So short-lived apps can definitely benefit from different types of JVM configuration. This is everything from memory to how big the heap is and making sure that your garbage collector is the right one. Normally, you don't need to mess with the garbage collector for short-lived applications. It's only for larger applications where the garbage collection algorithm that you use matters. So typically, just sticking with the standard G1, GC, or whatever is pretty good. But sometimes, depending on the application, right? If you're doing a lot of data processing, you have a lot of churn in your heap space and survivor spaces, having a parallel garbage collector could help with something like that, right? So that could be something like ZGC, which is introduced in Java 21, or Azul has we have our own garbage collector called C4, which is a parallel garbage collector. So those could also help for heavy data intensive applications. Okay. Right. So and long running apps can benefit. And of course, long running apps get more benefit from the JIT because the code execution paths get more efficient over time. All right. So I've already talked about this, so I'll skip it. Ready Now, CNC, these are proprietary products, so I don't want to spend too much talking about them. Okay. So let's take a step back from all the technical things that I've talked about and talk more about kind of more things that are general that you can do, right? So we talked already about over provisioning, right? We could be a little bit more risky and over provision less. So instead of over provisioning by 10 or 15%, maybe over provision by 5% and see if that works for your application and it doesn't blow up or have huge latency. Someone mentioned this at the very beginning. One of the biggest problems that we've seen when working with people is that folks just leave their VMs running in the cloud. They basically just have stuff running in the cloud that's not being used. So just shutting stuff off when you're not using it is helpful, right? So there's actually been a lot of discussion around this in terms of, how do we, like, not just for like production, but like all the way through the development process, how can we use less cloud? How can we save money on cloud? So here's a question for you. Everyone in here, I assume, has a CI/CD process, right? Continuous integration, continuous delivery process. Now, let's just focus on the CI part of it for a second. Should you do a new build and run all the tests and blah, blah, blah every time a developer checks in code? Right? How many people do that today? Okay, so that's quite a few people. How many people do it like every hour, half an hour, time-based? Did anyone do it time-based? Okay, one person. What are the strategies do you guys use for triggering a CI build? What other strategies do you use for triggering a CI build aside from just a commit or just, let's just run one every hour? What's that? Okay, type-based. That's an interesting one. Anything else? All right. So anyways, the crux of the matter is that especially for those of you who do a CI build and you do it in the cloud, right, where you're paying money every time a CI build fires up, maybe you don't do it on every commit. Maybe you do it, on a time-based, or maybe when you do it when you merge a feature branch into main or something like that, right? So again, those CI runs can actually add up to quite a bit of money because it takes a lot of time, especially for a larger application to compile, run, test, run integration tests, and all that stuff. So that leads us to the third bullet point here, which is lack of automation, right? How do we know that we're turning servers off, first of all, right? Do we have some kind of safety net there that says, oh, you've had this thing running for a while, but it doesn't look like you're using it. Maybe you should turn this thing off, right? So that's some kind of automation, or again, some scripts or something that you would write to check those kinds of things. And then, we talked a little bit about CI builds and continuous delivery or your CI/CD pipeline. Is there more automation that you could add to that so that that is used less and you pay for less horsepower on the cloud to be able to run those kinds of things? Okay. Now, the next two are more process and less technical things, right? Now, how many people in this room have a group or some kind of committee or whatever you want to call it that has rules for how you should be using your cloud as a developer, what you should be using on the cloud, how much you should be using it, rules around stuff like that? How many people have like that kind of body, right? So there's about 80 people in the room and about 10 people raise their hands, right? So that's about 1/8 of the folks, right? So for those of you who do it, that's great. For me as a developer, I hate it when people give me rules and tell me what I can't do, because I prefer just to do, what developers are kind of unusual people, right? We'll use the latest and greatest library. We'll throw it into our application and run it. But when it comes to running something on production, we're super, super conservative, right? So on one hand, we're like cowboys and rebels. We'll like do whatever we want to build our application. But when it comes to deploying something, we're super conservative. And the reason for that is obvious. We don't want our pager blowing up at 3 a.m. on Saturday and waking us up or whatever, right? We don't want to get in trouble by doing things that disturb production, okay? So something that we haven't talked about much is guardrails. I talked a little bit about safety nets before, but for those of you who are familiar, for example, with Cloud Functions, you'll know that Cloud Functions have a setting that you could give them that says, don't exceed this number of Cloud Functions for this specific application. So you can go literally, whether it's on AWS Lambda or Azure Functions or Google Cloud Functions, you can say, don't have more than 100 of these concurrently. So it's essentially a guardrail that says, for whatever reason, if something goes crazy or you just start getting a lot of load, you don't get this gigantic bill at the end of the day or at the end of the week or month because you just have all this, something has been hitting your cloud function unexpectedly and no one's keeping an eye on that. So you have a guardrail there, right? So there are ways that we can have guardrails like that for things which are not just built in. Right, so if you're doing, for example, Kubernetes and you're running inside of a large Kubernetes cluster and you do auto scaling, if your app scales and scales and scales and scales and scales, all of a sudden you're using all the resources in this Kubernetes cluster and probably need to have guardrails around that, right? So, and of course, the last bullet here is unexpected egress and ingress. This is basically data transfer charges into and out of a cloud platform. These can be extremely expensive depending on what you're doing. So it's just more than anything else, something to plan for, especially if you're an architect or senior dev on your team. What is it that we can do to make sure that we're not pushing too much data in and out? Of course, when you launch a new application, you have to push data in, or you're moving it from one region to another. You do incur this, but just to keep an eye on it and make sure you're not doing anything crazy. All right, let's spend a couple minutes in closing talking about a few random things. Now, I think this is the hardest thing to tackle, right? Is how do we architect a system that's able to handle non-uniform load? We talked about elasticity, right? That's one thing, but with elasticity, you have to have auto scaling, I think, and not some kind of manual thing that will scale down your number of servers when you're not using it. But then, what's the latency when you boot up a server and load comes in? How do you measure something like that? A lot of this is just a lot of developers just take a guess as to how big horizontally they need to scale up or even vertically scale something. But the ability to actually measure and know how much load your server can take and what actual production loads looks like, and then making some estimated guess in terms of how much you should scale your production system, it's usually a first step, because a lot of people just don't do that. You kind of just wing it by looking at what's on production rather than having a separate environment that helps you test that and do some estimation around it. Okay? All right, so we've already talked about this, who has load that's already consistent. Now, when I think about how much I should over provision, right, I typically use this graph. Right, so on the top left, I have SLA, or service level agreement. What's the complexity I introduce by doing horizontal scaling or adding other tools that let me have some flexibility in my environment, i.e. elasticity, right? So the SLA, I think, is a big one in here, right? So if you tell your customer that the maximum amount of time that it will take to return a user clicking on a button on your website is 10 seconds, is a lot different than having a response time of 1 second, right? Even though it's one order of magnitude, the time between 1 and 10 seconds doesn't seem that long. But again, SLAs determine a lot of that. Sometimes what you can do is if you can push an SLA to, let's say, from 1 second to 5 seconds to 10, 15 seconds, that gives you more capability in having less over provisioning. So what I mean by that is when your server starts to get to the point of being overloaded, if the requests take longer to return, and if it's okay to do that, then you don't need to over provision as much because you're still meeting an SLA, right? It's annoying for that amount of time for the user or your customer or whoever's using your application that it takes longer, but you're not over provisioning that, right? So anyways, I'm going to share this deck with everyone later so you can, this is what I used to think about it, right? Again, what's the SLA? How much can I over provision? Or how little can I over provision and get away with it? And what kind of complexity does adding elasticity and different tools around it add to my system? All right, so we got a couple of minutes left. Now, one of the things that I like quite a bit is containers as a service over Kubernetes. And that's primarily for simplicity, right? So this actually doesn't have that much to do with cost, right? But the way I think of a container as a service, again, that's AWS Fargate, Google Cloud Run, or Azure Containers, is basically here's a container, go and run it for me, scale it, and handle the bullshit so I don't have to, right? Which is kind of nice as a developer. But what's the problem with running CaaS versus Kubernetes or just a VM? Right. The problem is cost. A CaaS typically costs a little bit more than running Kubernetes and will cost more than managing your own cluster using VMs. Right. Everything in software architecture is a trade-off. Right. I really like cloud functions actually because they give you the ultimate elasticity. They can scale down to 0, so you have nothing running. Okay. But there are two main problems with it. The first one is on this slide right here, which is it requires a new way of architecting an application. Because when you build with a cloud function, what you're doing is you're not building an application by integrating code, right? Typically, what we do when we write applications, we open our IDE and we say we need a library to do a single sign-on. We go pull in a library and we write code to that specific library, i.e., we're integrating stuff or building features out at the code level. Whereas if you're using cloud functions, you're way up here. You're doing it at the component or modular level. So you have to think about serialization, deserialization, and now, cloud functions are supposed to be small. So you end up with hundreds of cloud functions. How do you manage those cloud functions? What happens if you change the interface for one of the cloud functions and these 10 other things depend on it, right? So when you're doing that at the code level, what you see is you'll see that actually breaks at the code level and you get a big warning sign about it in your IDE. But when you're doing it like that, using a cloud function, or for that matter, even microservices, how do you regulate that and make sure that changes over here don't affect all the other things that are using it because you're integrating at the component level? The second thing with cloud functions is that cloud functions can definitely be more expensive depending on what you're doing, right? There's a certain point at which cloud functions become much more expensive than just having a VM that is a fixed cost every month or every hour or minute, depending on how you think about that. Okay, final couple of things. I know we're out of time here. How many people are using Graviton in production to run a Java application? Okay, so that's 3 people in this room. All right. Now, what a lot of people don't know is that Graviton is way cheaper than x86 architecture for spinning up VMs in the cloud. Right, and of course, Java runs on virtually everything. So there are Java builds. Azul has Java builds, which are free. Our high-performance VM also has a build that runs on Graviton, again on ARM64 architecture, OpenJDK, etc. So, but just by switching from x86 to Graviton, you can save a bunch of money. Right? If you remember, very early in this discussion, we looked at the cost over the last 5 years, and there was that big inflection point where cloud costs became much cheaper, specifically because of Graviton. Right? It is much cheaper to run for compute specifically than x86 architectures. Okay, and then I don't want to go too much into this, but everything that you use in this cloud as a managed service is more expensive than doing it yourself. But again, where's the point? Where's the line? Or where does the I'm paying for expensive services which are managed versus it costs me this much to manage it myself? Where's that inflection point? That's what you have to figure out for your own application. A good example of this is, for example, if you're running Cassandra or Kafka, some big data infrastructure. Is it better to use managed Kafka or is it better to use DIY Kafka? That depends on how much Kafka you're using. If you're using a huge amount of it, it's probably better you manage it yourself because it will be way cheaper. Okay. All right. So that's pretty much it. I know we're out of time. The next presenter wants to come up, but I'll take some questions up here. So I thank you for coming to the session. I hope you enjoyed it.